Okay, so our key concept here. When net work is done on an object, we change the object's energy. We spent time on Monday and Tuesday laying out all these terms. Work, energy, power, etc., etc., etc. Well, today is the concept. Right? Now we've got good news and we've got more good news, basically. Right? This I do not think is very hard. And this is just another way of doing what we've already done. It's a different perspective of looking at stuff. It's a different way of problem solving. So the sheet in front of you is laid out two ways. It's laid out down a column. So we're going to go down the first column here on the left. And what we're going to see in the first column on the left is that using this principle is the same as using the stuff that we've already done and really focused on the past few weeks. Then we're going to go to the second side. And we're going to follow that same structure down the second column. But there's a difference between the first column and the second column. What's the difference in the layout of the first column and the second column? The peak column. The second column has friction. Right? And if you rewind, that's kind of like how we started talking about forces, right? Like we talked about forces with no friction along the tabletop to introduce some ideas. And then we added friction to it. Now, we might have spent a couple days talking about stuff with no friction and then added friction on for a couple days. But now that we've done that so much, we can do both of these ideas in one class period. So that's the benefit of spending so much time, what we've been doing over the past 6 weeks or so. All right? So, Justin pushes a 4-kilogram box along a frictionless surface with a horizontal force of 12 newtons as the box moves along the floor at a total distance of 6 meters. Now look at it. We're talking about work and energy, but it's still probably a good idea for you to draw a force diagram of the forces acting on the box as Justin pushes it. Well, if Justin is pushing this box along the floor, we've certainly got the weight of the box, and the floor has got to be pushing up, F sub n. And Justin, F sub j, is pushing, let's say, to the right. And those are the forces acting on the object. Now, how much work does Justin do pushing the box 6 meters? Now look, we know that Justin does work because the box has movement in the horizontal plane. The movement in the horizontal plane is parallel to Justin's force. Do the normal force and the weight force do any work? No, because they're not in the plane of motion. How much work does Justin do? How do we calculate work? It's the product of what two things? Perfect. Work is equal to the idea of the parallel force times delta x. Well, the parallel force in this particular case is Justin's force times delta x, which would be 12 newtons times 6 meters, or 72 joules. So if the surface is frictionless and Justin does work to push the box 6 meters, the 72 joules of work that Justin does goes into energy for the object. It goes to change the object's energy. In this case, it's changing the object's kinetic energy. 72 joules of work will cause the box to gain 72 joules of energy. Anybody got an idea how we can do number 3? Andy?
Kinetic energy formula.
Yeah, kinetic energy. Look at kinetic energy. Good job. Kinetic energy is 1/2 mv squared. So twice the kinetic energy divided by m square rooted is equal to v. Take your calculators out. We're going to do a bunch of calculations here today. So twice times 72 divided by a mass of 4, square root that. And oh, by the way, right, be careful of this square root. You just did this homework assignment. I take a look at him. There weren't many questions missed out of 50 kids. Right? That's 500 questions. You know, if we missed 20 questions, that's a lot, but probably 15 of them, we're forgetting to take the square root of this thing. All right, so twice times 72 divided by 4 square root, what's that give us? Yeah, 6. So the speed of that thing is 6 meters per second. So when Justin exerts a force over a distance, Justin does work. When Justin does work, Justin adds energy to the system. Based on the circumstances of this system, that energy was added in the form of kinetic energy, made the box go faster. How much energy did he add? He added the same amount of energy as work that he did. The result of adding 72 joules of kinetic energy over a distance of 6 meters is that the object was traveling 6 meters per second. Now, the good news is that's really just a different way to do stuff that we've already done. So if we look at the next couple of questions, that's going to illustrate that idea. Using Newton's second law, determine the acceleration of the object. Question 4. Newton's second law is sum of the forces equals m times a. So the sum of the forces divided by m is equal to a. What's the value of the sum of the forces based on this picture up here? Fj. The acceleration is just simply equal to Justin's force divided by the mass of the object, or 12 newtons divided by 4 kilograms gives me an acceleration of 3 meters per second squared. F equals ma. That's our last month plus of work. And that's one of the easier ones that we've done. Now, if we couple Newton's laws with kinematics, which again is basically what we've been doing for a month, you're going to see that our results end up exactly the same. So if we use the kinematics equation, in question number 5, to figure out how fast the object is going after 6 meters, well, what's the value of the initial velocity of this box? No. What's the value of the initial velocity? It starts at rest, correct? It's supposed to, all right? It's supposed to. So that box starts at rest. So if you look at that equation in question number 5, if the initial velocity reduces to 0, that equation just simply says v squared is equal to 2 times a times delta x. Or the velocity after 6 meters is the square root of 2 times a times delta x, which is the square root of 2 times 3 meters per second squared times 6 meters. What's 2 times 3? 6. Should not need your calculator for this. 6 times 6 is, square root of that is? Well, lo and behold, how does the answer to 5 compare to the answer of 3? The same, and it should be, right? It's only one thing happening. We shouldn't get a different answer if we calculate it one way compared to the other way. So we have this new concept. This is a new concept. It's a new way of thinking about things. There will be some problems that clearly call for this approach. There are some problems, that clearly call for this approach. There's also some situations where you can flip a coin and do either one. this is a good example of that. Okay? Now let's go to the right side. What's the difference between the right side and the left side? Got friction over here on the right side. But let's follow along from 1 to 9. It's basically going to illustrate a couple key points for us. Okay? How much work does Justin do pushing the box 6 meters? The same. Why do you think the same? Say it louder.
It's the same force acting over the same distance.
So I asked that same question the last period. They all started frantically on their calculators, writing stuff down, so on. They come up with different answers. They actually did some really, really good work. They just weren't answering this question. Physics' definition of work is super narrow. Work is the product of force and displacement. So Justin's work, I'm going to call that W sub J, is just Justin's force times delta x, which is what I have written right here. Whether friction is there or not, whether we put a squirrel on top of the box or not, none of that stuff matters. What matters to figure out how much work Justin does is knowing how big a force Justin exerts and knowing at what distance Justin exerts the force for. And the 12 newtons hasn't changed, and the 6 meters hasn't changed. So the amount of work that Justin does is still 72 joules. Now Justin's pushing the box, I'm pushing this chair. If I push the chair across the table, friction is also acting over that distance that I'm pushing the object. So if Justin pushes the box for 6 meters, friction is acting during those 6 meters. Right? So if I push this desk across the floor, I'm exerting a force for 6 meters. So is friction. Justin pushes the box across the table or the surface or whatever. He's exerting a force for 6 meters. So is the friction. So how much work does friction do? Well, the work done by friction is equal to the friction force times delta x. Just like the work done by Justin, this thing is like peeling off. Every time I open my mouth, I'm getting little fuzzies into my mouth. I lost my mask that I really love. I don't know where it is. So I got to deal with these things in my mouth. All right, so anyway, right? So just like Justin's work is his force times delta x, friction's work is the friction force times delta x. Well, we know delta x is 6 meters. Do we know the value of the friction force from this little write-up? No. But we do know that it's equal to mu times the normal force, always. We're in a better spot here than we were up here because what additional information do we know? We know mu. But does the write-up tell us about the normal force? No. Now, again, just like we have a force diagram over there, we should probably have a force diagram for the right side. That force diagram is the same as the left side with one addition. We need friction in the opposite direction, right? So W, Justin's force, normal force, force of friction. We don't know the normal force, but since there's no acceleration vertically, we know that the normal force is equal to the weight. And how do we calculate weight? M times G. So the work done by the friction is mu times M times G times delta x. How much work does friction do? Everybody got that number? 23.52. 23.52? Everybody confirm that? I don't really trust Miriam. 23. We're going to go 23.5.
All right.
Make it easy. You okay with that?
No, I'm very not.
red, what's the net work done on the box? Just as important as the number, how are we going to get the net work done on the box? Chelsea. Yeah, there's going to be a couple different ways that we can accomplish this. The first way is to understand that, hey, Justin does work in one direction, friction does work in the other direction. So to get the net work done, we simply subtract those two numbers. 72 minus 23.5, I believe, gets us 48.5. Okay, we are using this sheet as a means to communicate principles. So let's not lose track of those principles and only worry about the work that is on this sheet. Likewise, when we use this sheet to work through principles, we come across some key ideas and some key moments. This is one of those key ideas or key moments. Okay? We've dealt with this term, this idea of net before, right? We've dealt with it in terms of net force. Now first off, there are some synonyms for net force. And the summation of the forces, Charles, resultant force. Those are all synonyms. Now, how do we get the net force? Right? Force is a vector quantity, which means we have to take direction into consideration. So when F1 and F2 are in the same direction, we just mathematically add them. When F1 and F2 are in opposite directions, how do we get the net force? Subtract. What happens if they're at right angles to each other? We use Pythagorean. And any other angle, we use that C word. Components, right? Now look at, here's the thing. This works for any vector quantity. Oh, in fact, I keep wanting to show a video clip at the start of one of these classes. We went to Florida over Christmas break, walking through the airport, boom, bust out my phone, video my daughter on the People Mover. She was like super excited about that, right? Super excited at 6 o'clock in the morning or whatever it was, right? Because if I add two velocities together, if they're going in the same direction, we just add them. If we're going in the opposite direction, we subtract them. At right angles, we use Pythagorean, and we can do this for any vector quantity. But guess what? Work and energy are not vector quantities. They're scalar quantities. Now here's the thing though. This is the important part for us right now. It's a scalar quantity. So direction doesn't matter like it matters here. However, it matters in these two regards because we can have positive work and negative work. Work is a scalar quantity. This doesn't make any sense. Because if I've got work here and I've got work there, they're totally separate because of the definition of what work is. Work only occurs when I have forces that are parallel to the direction of motion. So this work and this work would be totally irrelevant with respect to each other. So work and energy are scalar quantities, which means plus and minus matter. Which means, basically, how much work did friction do? It actually did negative work. Now, Justin did positive work, positive 72. Friction did negative work. Somebody, well, everybody, I want to think about the situations. And somebody tell me an overriding rule that governs whether work is positive or negative. What's different about Justin's situation compared to friction's situation that could set up a guideline for us to figure out whether we have negative work or positive work? Carolyn?
If the work is done in the direction of the motion, then it's positive. If it's done in the opposite direction of the motion, it's negative.
Yes. Let me flip around just a couple words. Let's just go by force. If the force is in the direction of motion, then the work is positive. If the force is in the opposite the direction of motion, then the work is negative. And that corresponds to our change in energy. Elliot, come on up here. What's your name? Emmett. Zoe Snitzer's brother Elliot used to sit in that same seat.
Really?
Yes, he did. 2 years. All right, so look at it. Net work is equal to the change in energy. So a positive net work should result in a positive change in energy. That's logical, right? Look, if Emmett walks this way and I push him from behind, what do I do to his kinetic energy? I increase it. If I'm exerting a force in the same direction of motion, I'm doing positive work. I have a positive change in energy. Likewise, if he walks at me, right? He walks at me, and I do that, I'm exerting a force opposite the direction of motion. I'm taking away from his kinetic energy. I'm doing negative work to create a negative change in energy. Right? So that's a super big idea. How much kinetic energy does the box gain? Well, the net work is 48.5. Guess what? The amount of kinetic energy gained is 48.5. How do we figure out the speed after it's pushed 6 meters? Right here, right? Now, what do we know? When we calculate an answer for number 5, before we even calculate it, what should it be? What are some characteristics for it? It's got to be less than 6. Well, that makes sense because we're not plugging in 72 here. What are we plugging in for the kinetic energy? 48.5. So 2 times 48.5 divided by a mass of 4, square rooted is what? 4.9? Yep, that's what they got earlier. What's the speed of the box after it has been pushed 6 meters? 4.9 meters. Does that make sense? Right? How does that compare to across the way? It's less. Why does that make sense? What's friction's job? To oppose motion. If it's opposing motion, it's going to slow the object down. We're talking about the same stuff with different terminology, that's all. We can also use Newton's second law, determine the acceleration of the box. So if I'm down here doing question number 7, the sum of the forces equals m times a. So the sum of the forces divided by m equals a. This is what we did over here. Now over here, there was only one horizontal force. So that one horizontal force is the summation of the forces, or is the net force. Kaylin, what's the summation of the forces going to be based on this picture? Awesome. Fj minus Ff divided by m is going to be the acceleration. So what's that? 12 newtons minus, actually we haven't figured out the force of friction yet, but we can just put in mu times m times g, which is basically what we did right here. 0.1 times 4 kilograms times 9.8 meters per second squared divided by 4 kilograms. My acceleration is equal to what? Have we got that one? 2.02. Let's just stick with 2. All right, Zach, I haven't heard from you yet today. Why does it make sense that this acceleration is 2 meters per second squared? Relative to the column on the left, why does it make sense? What's the acceleration in the column on the left? 3. Why does it make sense that this is less than 3? Because there's friction. Justin wants to accelerate the object. Friction is saying, nope, not going to happen as much as if I weren't here. How fast is this object going? Hey, what answer should we get for number 8? We should get 4.9. We're going to get 4.9 the same way we came over here. Instead of 2 times 3 times 6, what are we going to have over here? 2 times 2 times 6. Square root of that is 49, or 4.9 rather. And again, how does the answer to 5 and 8 compare? They're the same. Now, one last thing here, okay? How did we figure out, I'm going to get rid of the screen. I'm going to get rid of the screen so I got more board space. How did we figure out net work? We did Justin's work and got 72. We did Friction's work and got 23. We subtracted them to get 48 and a half. Okay? Now, there's another way. It's really the same way. Look at, if work is the product of F parallel times delta x, then, the work that Justin does is equal to Justin's force times delta x. As long as Justin's force is in the same plane as motion. That's that. And the work that friction does is equal to the friction force times delta x. And if Emily were doing work, the work that Emily did would be equal to Emily's force times delta x. So if we're trying to find the net work done, then we would put the net force in that calculation. Well, based on this picture, Kaylin, what's the value of the net force acting horizontal? Yeah, you already did it once. That's why I called it on you again. Right? The net work done would be Fj minus Ff times delta x. Look at it. What's that? Hey, that's Fj times delta x minus Ff times delta x. Where did we already do that? We took this and subtracted that. That's this. So it's really just like one big cycle of stuff. Okay? This is our main principle. Now, your homework that's due on Monday, we're going to get to a couple of the nitty-gritties there. All right? But again, let's think about this. If I am going to push this thing across, the net work done adds kinetic energy to this thing. Well, if I do work vertically, what type of energy am I changing? Gravitational potential energy. So if I did 20 joules of work to lift this thing up, what's the new gravitational potential energy? 20 joules. And likewise, I lost my rubber bands. If I stretch a rubber band by doing 40 joules of work on the rubber band, guess what I add to the rubber band? 40 joules of elastic potential energy. No matter what form the energy takes, this principle always holds true. And this principle is really just another way of working with Newton's laws. So it shouldn't be too difficult, right? Obviously,